Hello class, this is CSE-5250, Section 1, Week 13, Spring 2023. This is going to be part 2 of the video that I had put out last week, which was the step-by-step process of how we can build up the sieve of Eratosthenes and we want to use MPI to parallelize it. So let's recap with where we left off from there. And I have a PowerPoint presentation for this. Come on, work with me here. Okay. As a recap, implementing the sieve using MPI requires some thinking, but it is possible. So, rank 0 sends an array of numbers to all other processes using a for loop. All other processes then cross out multiples of the number 2, except 2 itself, from the vector it received from rank 0 using a for loop that skips some values. It's going to skip values, but each process is going to skip values, but together they're going to cover the entire array. Those processes then send back their modified vector back to rank 0, and rank 0 has to read those returned vectors to find out what numbers were crossed out, so rank 0 can update its vector with all the crossed out numbers, so it can do that process again for the next prime number. What we're gonna do is implement code that would not only do the number 2, but it would do the next prime number after that. It would basically do this entire process for the next prime number, and the next prime number after that, and the next prime number after that. Because the first prime number is 2, that's what I had shown back in part 1. But now we're going to get ready to basically do this entire process for all of the prime numbers from 1 to 10. Okay, so here are the steps. Iterate through an array of numbers and cross out any non-prime numbers. We're also going to ignore the number 1. We would actually cross that out because it's non-prime. If you find a prime number, have rank 0 send that prime number to all other processes. All other processes then finds multiples of that prime number in parallel, and then it's gonna send those numbers back to rank 0. So rank 0 is going to send not only the current prime number, it's also going to send the entire vector of numbers. All other processes are going to use that information to cross out some of the multiples of that prime number, but combined, all of the processes are going to cross out multiples of that prime number. What rank 0 has to do is it's going to receive those modified vectors back from all the other processes, and then it's going to combine its vector with the received information to update its vector so that all of the multiples of the current prime, except for the prime itself, are crossed out. We did these 2 steps back in part 1, when the prime number we only ever had to consider was the number 2. Now we're gonna do this step where we go through the array and find those prime numbers. So we're basically starting again. Again? Yeah. So first off, if you followed along back in part 1, save your work now, because we're gonna copy paste parts of that into here. But we're going to start over again. Rank 0 is going to create. No. So here's our starting point again. We have a vector of numbers. The vector is of size 10, and it's full of zeros. Rank 0 is going to fill that vector with all the numbers from 1 to 10, and then it's going to cross out the number 1 because it's not prime. We're going to simulate what would happen if the multiples of 2 were already crossed out. So to do that, we can just say numbers 3 equals 0, numbers 5 equals 0, numbers 7 equals 0, and numbers 9 equals 0. So what these are? Those are what 3, 5, 7, and 9 are indices for the numbers 4, 6, 8, and 10. We're going to iterate through the array of numbers, or I guess it should say vector of numbers, and then we're going to send that to all other processes. So we have a for loop. We're going to store the current number in a temporary variable. Current number equals numbers I. And then, using another for loop, we're going to send that to all other processes. MPI send address of current number is the first argument. Second argument is 1 because we're sending one thing. Third argument is MPI int because the data type is an integer. Fourth argument is going to be the rank of who's receiving the message. And the last two arguments are 0 and MPI com world, because we don't have to worry about this for now. It could also work if we sent the address of numbers I. That could work too. This is just more readable. For the else code, because rank 0 is iterating, it's going to send every number from the numbers array. What the else code here, it has to iterate the same number. It's going to iterate for the same number of loop iterations. So for int I equals 0, numbers.size, because here both rank 0 and all the other processes, they have access to this. They know that this is a vector of numbers that's of size 10. So for now, we can just use this. Int I equals 0, I is less than numbers.size, I plus. We can declare a variable called received number and store the incoming message in that variable. So MPI receive address of received number, 1 because we're receiving one thing, MPI int because it's an integer, 0 because rank 0 sent the message, and then 0 MPI com world, MPI status ignore. So here's the thing. What the outer for loop in the sieve did was iterate through the array looking for prime numbers. It only executes its inner for loop if the current number is a prime. And we denote non-prime numbers, or rather, we denote non-prime numbers being crossed out as replacing them with the number 0. So, if received number does not equal 0, that means we have found a non-prime number. That's actually gonna be our trick here. We only do something if the received number is not 0. And that something for now is going to be rank 0 received a non-zero number from rank something received a non-zero number from rank 0. So what I said is going to apply for what this code does is does something if it receives a non-prime number. However, some of these numbers aren't really non-prime. The number 9 is not prime, but just roll with this as an example because we will get to crossing out multiples of all the prime numbers just soon enough. So, if we just take this code here and add in all of this code, what we can do is this. This is kind of like a cooking show. I had already prepared all the code ahead of time. This is a step-by-step thing. So what I'm going to do is go into Visual Studio and show you what this program looks like. Give me a bit. Right, so we're in Visual Studio. Control-Shift-B to build. This is all the code that was described in the PowerPoint previously. So we build, I'm going to close this for now. So right-click. Open in File Explorer, go back one folder, enter this debug folder. And then we have the executable here. We can't just run it by double-clicking it, nor can we debug the program using the debugger. So you have to click on the address bar, type in cmd, press enter, and then we have command prompt ready to go. We type in the command, mpi exec -n. We're going to use 4 processes for this, and then we're going to type in the name of the executable, which is mpi sieve spr2023.exe. And there we go. Rank 1 received a non-zero number from rank 1 received a non-zero number, 23579. Rank 3 received a non-zero number, 23579. Rank 2 received a non-zero number, 23579. So it worked. So that's the next step. As I said, 9 is not a prime number. So technically this code is already wrong. But again, this is for demonstration purposes. We will get around to crossing out that number 9. So what's the next step? Well, let's go back to the PowerPoint. I also put checkpoints in here. So if you look at this checkpoint and what we have in our output here, it matches. Nice. So the next step is to consider this. Why stop at 10 when we can search for numbers for up to any maximum? So this is the point where we can replace the number 10 with any number we want. We do that by introducing a variable called searchmax. Searchmax is back. So we can set this to any number we want. Let's set it to 100, because why not? We can set this to anything we want anyway. So when we declare the vector of numbers, instead of having in the constructor the arguments 10 and 0, it's going to be searchmax and 0. We're also going to make another change. We're going to swap out searchmax. No, we're going to swap in searchmax for every instance of numbers.size. This is just to make things cleaner. Though, if you recall, the outer for loop of the sieve of Eratosthenes, for mathematical reasons, that only has to go up to the square root of the search maximum. We'll cycle back to that later on. So, this is the part where we start copy-pasting code from part 1 into part 2. So, here's the code for rank 0. We're gonna make a few modifications, so we have this code to start out with. The algorithm for the sieve, as a nested for loop, had the inner for loop be parallel, but it only had to execute if the outer for loop found a prime number. Rank 0 can send the current number to all other processes, but if it's not prime, nothing needs to be done, so it'll just skip to the next loop iteration. And if that's prime, then it'll do something. So, in here, where my cursor is at, if current number does not equal 0, we do something. And here's what that something is. We're gonna take some code from part 1 and directly copy paste it into here. Rank 0 simply needs to send it. So basically, the process of where rank 0 sends its vector of numbers to all of the processes for a for loop, and then it's going to receive the same vector but modified from all of the processes, and then it's going to go through a for loop where it iterates through the received vector, and basically anywhere there's a 0 in the received vector, it's going to copy that to its rank 0 is going to copy that to its array of numbers. So all of those steps are going to be copied into here. If current number equals 0, we're going to do all of those steps. We're also going to want to comment out a few printf lines, because at this point we're going to scale up and the printf is going to get in the way. For the else code, it's also another copy-paste. So, back in part 1, the code for all other processes was this. It's going to receive a vector of numbers, but it's going to store that in its own vector. It's going to calculate a starting index based on the current prime, and it's going to calculate a stride also based on the current prime. It's going to use that. It's going to use those values as part of its for loop. So, effectively, all of the processes will be skipping each other's work, but combined they do all the work. Again, all of this was from part 1. And then after that, it's going to send that modified array of numbers back to rank 0. We're also going to want to comment out some printf statements, because, again, they're going to get in the way. We're scaling up, so we don't want to accidentally spam ourselves. However, at the end of the code block for rank 0, what we want to do is to add in one more for loop. This code here is basically all from this page, but it's collapsed. So after all of this, we're going to add in another for loop. And this is to signify the end of the sieving process. At the end, we're going to print out all of the numbers except for those that have been crossed out and replaced with 0. So if this works, we're going to have all the prime numbers. So what I'm going to do is I'm going to go back into Visual Studio and I'll basically get all the code I described in here set up. Give me a bit. Okay, got the code all set up in Visual Studio. We have all the changes that we have. Search max is not 100, but again, we can set that to anything else we want. I've copy-pasted all the code that's needed. And now, if we build, it should have built by now. Yeah, it built. It's just pretty quick. Now, since I already had opened command prompt, I'm going to press the up button a few times to get the command to run it again. And 2, 3, 5, 7, 9, 11, 13, 15, 17, 19. You see the problem now? And if you look in the PowerPoint, the checkpoint says it didn't quite work. And that's because the code that we copy-pasted, it was stuck at only crossing out the multiples of 2. So we have to go back in and make a few changes. And here's what those changes are. For the else code, we were now receiving the current prime number. But in the copy-pasted code, we had already set the current prime to be 2. So, as a super duper quick fix, let's replace current prime. Instead of current prime equals 2, it's current prime equals received number. So, if I look back at the code, current prime equals 2, current prime equals received number. That's not the only change though. We have to calculate the starting index as well. The current prime, for a current prime p, because of how the indices are set up, because everything is sequential, because everything goes up by ones, except the index starts at 0. If the current prime is p, its index is actually going to be p minus 1. So we can calculate the starting index to be current prime minus 1 plus rank multiplied by current prime. So current prime minus 1 plus rank times current prime. So we're basically using the current prime as the calculation for the starting index. So I'm going to copy current prime. There. Current prime minus 1 plus rank times current prime. Thing is, we have to do a similar thing for rank 0, because it also has a current prime and starting index calculation. The current number, we have it here already. So current prime equals current number, starting index is going to be equal to current prime minus 1 times current prime minus 1 plus I times current prime. And if we go back to the PowerPoint presentation, it's going to say exactly that. So we have to do a similar fix as we did in the else code. So if we build this code instead and run it, now it works. Now we have all the prime numbers from 1 to 100. So it basically works. Pat yourself on the back, because we have now successfully coded the sieve of Eratosthenes using MPI. A few loose threads though. No pun intended. The original sieve relied on a nested for loop, or the outer loop, iterated to the square root of the maximum number. So basically what we can do is do one minor change. So this for loop here, it's actually going to correspond to this for loop here. They go up to the same number, which is search max. What I'm going to do is add in, I'm going to include the library math.h, and then I'm going to calculate the square root of the search max. And it's going to be cast to int square root and then search max. I'm going to copy this value here, paste it into here. It would probably really help to zoom in here, though. I hope you saw that, by the way, because I can't get a good position for my face cam, but because it may have covered up some of the code that I was writing. So include math h. We're gonna calculate square root of search max, and we're gonna replace for this code here where we have iterate through the array of numbers. No. We only have to go up to the square root of search max. So copy that. This for loop corresponds to this for loop, square root of search max. Rebuild. See if it works. The thing was open already, so there we go. Works the same as before. Okay, so there is one other loose thread. Actually, there's several loose threads. We can do a little bit of cleanup, where every instance of numbers.size, we are going to replace that with search max. Again, this is just to make everything a little bit cleaner. The temp vector that rank 0 has to create is also of size search max. So we can replace every instance of temp vector.size with search max as well. That would be done for both the rank 0 code and the code for everything else. So temp vector.size is going to be search max. Temp vector.size is also search max. Numbers.size is search max. Any instance of that, I'm gonna replace with search max. Numbers.size becomes search max. Numbers.size becomes search max because here we are. Numbers.size equals search max because search max is gonna be something that both rank 0 and all the other processes will have access to. So if I build this again, unless I screwed up with copying and pasting, if I run this again, there we go. It works again. So why stop at 100? We can go up to, let's go up to 10,000. Build. And run. There we go. A whole bunch of prime numbers. Just like that. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, all the way to 9,973. I guess 9,974 to 10,000, those are all non-prime numbers. Okay. Some loose threads. So, there is one other weird thing. You know how in here we had a for loop that has for int I equals 0, and then here we had a nested for loop for int j equals 0, but this isn't. But actually, no. We had a for loop with like for int I equals 0, and then we had another for loop in there that was also for int I equals something, and then for int I equals something again. It turns out that we don't have to swap these variable names for something else, because this I is actually going to refer to its innermost scope, which is going to be this code block here, because we have the I defined here. So this I refers to this I. So this I is actually not going to refer to this I here. So that was one thing that I always found that concerning when it came to for loops, but basically it's a non-issue altogether. It only becomes a problem if you need like I, J, and K. Like, for example, in a triply nested for loop, if you need if you have a triply nested for loop, such as with matrix multiplication calculations, you would need all three iterators from all three for loops. So I, j, and k. So they all have to be unique. Here, they don't necessarily have to be unique. Or rather, I should say, they don't have to be unique at all. As long as you know what scope these i's belong to. So this I belongs within this code block. So this I is going to refer to this I. So that was one loose thread that I felt like it might have been worth mentioning here. And again, that's a slide in here. Okay, as I said, we can also replace all the instances of numbers.size with search max and temp vector.size with search max, because nearly all of these arrays, basically all of them, will be the same size. So you may as well just use search max. I do have an alternate implementation where instead of having an array be sent to a process, having numbers crossed out and sent back, instead of that, I have the alternate implementation where rank 0 says we're casting out multiples of this number. And then all the other processes are just gonna basically compile a list of indices of non-prime numbers, send that back to rank 0. So rank 0 can basically iterate through the array of indices and cross out numbers based off of that. I do have the alternate implementation here, so if I just, here we are. This is an alternate implementation. You don't have to do it like this, but you are welcome to try it. The thing is this. As it turns out, the only thing that's necessary is for all other processes to send the indices. All the other processes, they only need to send the indices. They don't need to receive anything from rank 0 other than the current prime. That's it. So it would be redundant for rank 0 to send the array of numbers. But the principle of having to send and receive vectors still applies. It's just a little backwards. Instead of rank 0 sending an array to all the processes, we're still going to have the situation where rank 0 has to receive from all the processes. But it's not going to be the entire array of... It's not going to be the entire array, though. It's just going to be just an array full of indices. That's it. So that's the alternate implementation. If I build that, what should happen is more or less the same thing. If I clear and do that, okay, so hold on. I actually have the code here, so replace that. Okay, so the search max was already set to 10,000. Let me just double check. CLS, run it again, and it runs the same as before. Different implementation of the same thing. So you can do it. So if you're following along with this tutorial, you can do it either way. So move my face. Yeah, you can do it either way, where we have this implementation here. Excuse me. You can have either this implementation where it's a vector being sent back and forth, or the other implementation where it's only just no back and forth between vectors, just vectors only being sent from all of the processes back to rank 0. So there's no more back and forth in this alternate implementation. So, with all of that done, how do we benchmark this? All right. this is where the PowerPoint stops, and I'm gonna get a little off script here because, okay, I've already prepared the code for data collection. So here are the modifications we have to do. Let me move my everything. So, whoops, hurry up. Okay, so slight change to this arguments here. So int argc, comma, character star, argv. So 2 stars. So here's the change that we're gonna do. If you want to do data collection, we need to include standard chrono. Using namespace standard chrono. So, how do we time the sieve of Eratosthenes if it's going to be spread among multiple processes? Well, one thing we can do is consider the fact that rank 0 is basically telling a bunch of other processes what to do, and it's going to be waiting on all those other processes for something from them. Here I set that to 1 million, that's 1e6 here. I'll explain what this is later on, but basically, we can have auto start equals high resolution clock now at the beginning here, and then auto stop and auto exec time within the code within the code block for rank 0. So instead of printing these out, what we can do is see out the execution time. And it's set up such that only rank 0 gets to print out the execution time. And that's because rank 0's only main bottleneck is waiting for something from all the other processes. So we don't really need to time all the other processes, we just only have to worry about the main process, that's rank 0. So if I build this, clear, and run again, now I get an execution time. Found prime numbers up to 1 million in, what is that, 1.2 seconds? Yeah. And then we can run this again, and again, and again. We can also try it with different process counts. Here's the thing though. When you call the MPI exec command, what you need to pass in is how many processes you're going to use. So we have it already set to 4 processes. Let's set it to 16. It executed in about the same time. So what that tells us is, and we may need to run this again and again just to make sure, we were getting some diminishing returns already at 4 processes. So if we did this with, say, 2 processes, it's going to take longer. And we can run that by running it again and again and again, just so we can build up enough data to take an average. So, in another video I explained how we can, at least with Windows, on Windows-based systems, I explained how we could automate the process of data collection. So, one thing we can do is going to mimic something that I've shown in a previous video. So, let me open up this here, because I'm just gonna more or less copy the code from that. Okay, so if I want to write this all to a file, I'm gonna need to include fstring. And if I want to write this all to a file, I'm going to delegate, what I'm going to do is have that write to a file business be done by rank 0. Only rank 0 is the main process here. So, only it can write to a file. So, the super duper easiest way for that is to basically look at some code from the OpenMP sieve that I had earlier. Here we are. So I can just, so basically you can just copy all of that and paste it in here. Build. And because I have this already opened, clear, run. Now what should have happened is an output file should have been made. So let me just make sure that that had already happened. Okay, you want to know where the output file went? It's in the same location as the exe file. So if I open here, if I open this, in Windows you can click View and you can toggle the preview pane so you don't have to open this at all. So you can open it in the preview pane, and here, found prime numbers up to 1 million in 1.6 million microseconds. So we can run this again and again and again. Now, of course there's a problem because every time we do this, it's gonna overwrite the contents. That's not what we want. So we're gonna have to modify the code here so it doesn't overwrite everything we've ever written. So I'm gonna modify this so every time it writes, it's gonna... Actually, what I'm gonna do is a few changes. And we can do this however we want. This is just one way we can do data collection. The other way was how I might have described it in a previous video. We create output files where every combination of we write output files for every combination of search max and process count. So that way we have output files for, we have separate output files for everything. So let me just modify this so instead of writing everything, it's a little bit more descriptive. So give me a minute. Okay, so I'm back. I ran it a few times and I got it to successfully work. So here I changed the output so that not only does it print out the execution time, it also prints out how many processes were used. And if we go back to the folder that contains the executable, I have the output file here, the output.txt. If you look at the preview pane, here, found prime numbers up to 1 million in 1.69 seconds using two processes. Again, we can go back in and change the process count to whatever we want by changing this one argument to anything we want. And now, found prime numbers up to 1 million in 1 second using 16 processes. Okay. So, if you look back in that one past video where I talked about how we can automate the process of data collection, I talked about how we can use a batch file for that. So we can just click the batch file and it will do literally everything. You can just walk away from your computer, have it run, hope that the power doesn't go out, and when you come back, after however many hours that process would take, or you could just, for example, leave your computer running overnight, at the end of that entire process of running processes for however many trials that we want, at the end we should have one file, or, if you recall back to that video, a bunch of files containing all of the execution times for every trial that we want. So we can, again, we want to do several trials so we can get an average execution time, and then we can do all sorts of data analysis on it. Right, so one other thing to do that I have shown before is this. This is the sieve that I had wrote from when I first took parallel programming. I have this int argc character argv. Here I had passed in the search max as a command line argument. what I'm going to say right now is that we can do the same thing for the MPI sieve. So here's what that looks like. So it turns out I had already written this up already. So I'll copy paste that and paste it in here. So I had to make a few slight changes here that you can't really see because of my face cam in the way, but here it is. Int main argc character star star argv. That was slightly different from how it was set up previously, where it was like int star argc and character star argv. But here's how it works. If you want to specify how many, we're already specifying how many processes we want just using the npi exec command. If you want to specify the search max by passing it in as a command line argument, here's how. If argc equals 2, search max equals a to I argv1. So, see this command here, where I have been typing out npi exec -n16 npi name of the executable. If I am to type that, but I instead do this, hold on, I'm gonna build this. If I have to add the number 100 after the executable name, that's going to correspond to argv1. So that's literally argument 1. And I enter that. It broke. That's not supposed to happen. Hold on. Let me go fix this. Okay, I'm back. Apparently I don't know what I did wrong, but apparently I got it fixed again. I guess it's sometimes that's the reality of programming. You fix something and you don't know how you fixed it. But anyway, it works now. So if I am to type in the command again, this is for 16 processes looking for primes up to 1 million. We get an execution time of 1 million microseconds. And I can run this again, and again, and again. And that's because I am passing in the search max as a command line argument, and it's being parsed in here, so that way, here the search max is 1 million, but I'm basically overriding it to be whatever I want. So if I type in 1000, it broke again! What? So, in principle, this is what we should be doing, passing in the, in principle, what we could do to automate the entire process is to just use a batch file that would call this command, and, here. But somehow it isn't working. But I think what happened is it's because the number of processes is a little bit too big, so maybe if I CLS, do that again, because I did test this out, and it did work for process counts that wasn't 16. So maybe we have to do something. So if you want to automate this and you're getting a few hiccups like what I have right now, the next best thing is to just do it manually. Next best thing is to just do each thing manually. So each combination of search max and process count, you'd do it manually, but you'd still be able to just call a batch script to write everything into just one file. Speaking of writing into a file, I wrote in some code here that will write into a text file. It will append to the text file found prime numbers up to search max in execution time microseconds using column size amount of processes. So if I build that, and if I do this again, using 8 processes, so what's going on is because I'm passing in the search max as a argument, I can set it to whatever I want, and it will just work. Except for if I trying it with 16 process. If I did it with 15, somehow it works. But not with 16, I don't know why. Okay, now it worked that time. I have no idea what happened. It was crashing, and then it wasn't, and then I have no idea. But anyway, this is what you would do if you wanted to automate this. If you have a batch file, then, as I said, you can just write a batch file, not unlike, you would write a batch file not unlike, hold on. You would write a batch file that isn't unlike this. If I open this with Notepad++, you'll see this. So, for /L%%x in 1,1,100 do npi exec-n1 and then executable name, and then this final argument here is the search max. So you would do something not unlike this. You would write this into a batch file, and then you would either end up with a whole bunch of execution time files or you can have it just in one file. Either way, you would automate this whole process so that after you run this overnight for or however long it would take for you, you can just copy all of these numbers into an Excel spreadsheet and find the average, and then you can populate an entire table of execution times. One other thing. Because this sieve, that's not it. Because this sieve requires there be at least one other process for rank 0 to talk to, the minimum number of processes for this to work is actually 2. So the 2 process case is actually it's gonna be as though it were a 1 process case. So if you're to do your benchmarks, you can't start at 1 process because rank 0, as it's coded like this, will have no other process to talk to. So, at least if you're to program it the same way that I have shown in this video and the last, if you have a different way of programming it so that rank 0 will always do something alongside all other processes, then if you can do it that way, then feel free to use that implementation. But anyway, if you have it such that rank 0 needs to talk to at least one other process, you need to start your benchmarks not at 1 process, but 2 processes. Other than that, you can basically more or less follow the table that I have in set for the OpenMP sieve benchmarks. But as I said, over sometime after I upload this, in the coming days, I will put out an assignment. That's going to be your final assignment. It might not necessarily your last assignment for the entire course, because I have plans for one final short answer question. But that's gonna be for week 15 though. In the meantime, go through the video, go through the last video. I would advise you to get started on the MPI sieve as soon as you're able to watch this video. We don't have a class meetup next Monday because I'm going to be out of town. So the soonest you can ask questions to me in person will actually be week 15. So email me if you have any issues or problems or anything like that. Follow through the video, get as far as you can, and once I have the instructions up for the MPI sieve, that's your final. So, that's gonna be it from me. If you have any other questions regarding anything, again, you are always welcome to email me or message me on Canvas. But that's gonna be it for this video. We'll meet again on week 15 for the final time. I will put out one other video. I have plans for at least one more video for the course. That'll just be a quick introduction to NVIDIA CUDA, because it turns out the CPU is not the only piece of specialized hardware meant for parallel computing. Depending on what kind of computer you have, or if you built your own computer in the last few years, there's a really, really good chance that you put a graphics card into your computer, and that's basically another piece of hardware for which you can do all sorts of parallel computation. So, really quick intro on NVIDIA CUDA sometime next week, and then we'll meet again on week 15 for the last time to finalize everything, and then I'll give you your final short answer questions in. So, that's gonna be it from me. If you have questions, email me or message me, and that's basically it. Alright, that's the end of the video. Alright, thank you.